Yeah, so it gives me great pleasure to give this review talk here. I'm going to give this review in the frame of the paradigm that's been built up over the last few decades on what debris disks are. But I'm going to be also focusing on some of the results coming out from lots of people. These I should point over here, shouldn't I? These early career researchers, many early career researchers. I'll be highlighting them throughout the talk, but of course the work that I'm going to be talking about is the work of many people, given this is a review. So let's start off by getting everyone on the same page about what a debris disk is. So a debris disk is not a protoplanetary disk, which is what Fazana was talking about before, but it is a descendant of a protoplanetary disk. So protoplanetary disks around young stars, and then after that disappears, stars left with a debris disk, and we can use debris disks to tell us something about the processes that are going on in protoplanetary disks, the planet formation and planetesimal formation and protoplanetary disk dispersal, for example, and I'll be using that at some point. The other perspective is that a debris disk is just a component of a planetary system, and it is essentially anything that you find around a star that's not a planet. So it's the asteroids, comets, and the dust and gas that comes from them. In the solar system, that would be the asteroid belt and the Kuiper belt and the zodiacal cloud. So also, to get everyone on the same page, how do we get information about debris disks? There are three types of observations that we have. We can look at a star photometrically, and in that case, we will see these photometric observations. These are all observations of the same star, Fomalhaut. We will see the photosphere of the star, but then we see this extra emission, and this comes from dust that's heated by the star and then re-radiates the emission in the infrared. And that's how we discover pretty much all debris disks are discovered photometrically. But for the ones that are near enough and bright enough, then their disks can be imaged, and we can image them because they're nearby at exquisite resolution, down to 1 AU resolution. And we used to think of debris disks as being gas-poor counterparts to protoplanetary disks, but over the last decade, we've discovered that many of these disks actually have gas associated with them that we can detect through line emission. So what is the paradigm? Well, the paradigm is that, as you can see, these debris disks look like rings, and the dust is replenished by the breakup of planetesimals. So the paradigm is that there are planetesimals orbiting the stars in belts that collide, and they get ground down into smaller objects that collide, that get ground down into smaller objects, setting up a collisional cascade that goes all the way from big objects down to the smallest dust, and that dust then is affected by radiation pressure that ejects it onto hyperbolic trajectory. So it's when it gets down to micron-sized dust, then it's removed. And because mass is being removed from the belt, and we know that the mass loss rate is going to scale with the square of the mass of the belt, then we can get a very simple equation for how the mass of the belt evolves with time. It essentially stays constant and then falls off as 1 over age when the biggest planetesimals in the disk start to collide. So what's the paradigm? Well, the paradigm that explains all of the photometric observations that we've taken over the last 20 years is that all stars are born with a planetesimal belt, and that then evolves due to this steady state collisional erosion. But the different stars have belts that are born with different radii and with different initial masses. They're just drawn randomly from some distribution. And with that paradigm, then we can explain all of these observations from Spitzer at 2 different wavelengths. The black dots are the observations, and the yellow dots are a population model based on that paradigm that fits very well with how they get fainter with age. And another way of looking at this, so that was based on Spitzer 20 years ago, and another way of looking at this is shown on the right, the unbiased surveys of the nearest 500 stars that we did with Herschel. This plot summarizes all of those results, which the color scale shows the fraction of stars that have debris disks in different parts of parameter space, where the y-axis here is the luminosity of the debris and the x-axis is the temperature. And the disks lie exactly where we expect, because they don't lie below here because they'd be too faint to detect. They don't lie above here because you'd have to put too much mass in the disk for it to be plausible. And importantly for the paradigm, they don't lie above this line because they might have been born with disks that were up here, but over giga-years of evolution, then they would all have been depleted down to be below this line. So we can explain all the photometry. How do we get more information out of the disk? Well, we do this with imaging, and we'd always had images of debris disks going back 40 years ago. The first one was detected. It took 20 years to get another image of a debris disk, and we now have many more. But we're now doing this systematically, and a program we just completed that was led by Luca Matra was to systematically observe all of the disks that we could observe, feasibly resolve with ALMA. It's a program called Reasons, and that has ended up with this gallery of 74 planetesimal belts, all resolved. And these have all been, first thing to do, rather than looking at the high resolution structure, which I'll show you in a minute, is to fit these all systematically to work out what the radii of the belts are and what their radial widths are, and also their vertical heights, because that can tell us something about how they formed. And one of the results that came out of this is that the radii of the belt scales with the luminosity of the star. It's not a direct one-to-one correlation, there's a scatter around this, but the disks around higher luminosity stars are larger, and this is indicating that the location at which planetesimals form in the disks is related to the temperature in the protoplanetary disk. So for example, it could be that planetesimals are forming at the locations of snow lines in the disk, where the volatiles condense into ices. And this begs the question of whether the location at which planetesimals form, where these debris disks are seen, how that connects to the structures we see in protoplanetary disks. Because as Fazana was showing us, we see all these very high resolution structures in disks. The protoplanetary disks are broad, but they're broken up into multiple narrow rings. And that's what's summarized on this plot here, which shows the radius of the belts and the fractional radial width. And in blue is shown the debris disks, where the planetesimal belts seen around all the stars, and the structures seen in protoplanetary disks. And you can see that in terms of the radii, where the planetesimals are, their radii are very comparable between the protoplanetary disks and the debris disks. But the one place where there's a difference is in the fractional width. So the debris disk, where planetesimals end up forming, are over a much broader area, for a broader range than the location of the concentrations of millimeter-sized grains in protoplanetary disks. And this could indicate, for example, that these concentrations we see in protoplanetary disks are the sites at which planetesimals are forming, but that those locations might migrate over time during protoplanetary disk evolution, and so forming planetesimals over a wide range of radii. But there's a caveat, because that Reasons program was only aimed to resolve the disks to work out what their radii was, and it wasn't to get high-resolution structures. So that led to another program, a large ALMA program called ARCS that Seba Marino is leading, that aimed to get high-resolution structure. And I'm going to show you some of the results from this. The program is almost finished. We're imaging 18 disks, to which we can add 6 from the literature, and we've got data for all of them apart from these. We're still waiting for some high-resolution data from these to come in. But I'm going to show you some of the early results from this that will be coming out over the next year. So the first thing to look at is that radial structure. Do these broad disks, for example, do they break up into multiple narrow rings when we observe them at high resolution? Well, the answer is, well, to some extent, maybe. So some of them yes, some of them no. But what we do see from these radial profiles is that it's much more complicated than saying that these disks are just narrow rings. So we see a range of structures. These are the face-on surface brightness profiles from the disk. This is work of Yino and Jeff, because this has to be deprojected because many of these disks are edge-on, and also deconvolved. So it's a large piece of work. We see that some of these disks are very broad. They extend over a large radial width, but most of them are not actually broken up into multiple rings. We would be able to detect that for all of these disks, but then some of them are. There are narrow rings within some of them. Some of them do look like they might be. The broad disks might have belts, but then they have these very shallow outer edges. Some of the disks are narrow rings, very narrowly confined, But now if we look at very high resolution and high sensitivity, we can see that some of these are narrow rings, but they have these halos that extend out to several hundred AU. So what are we learning from these radial profiles? Well, these tell us where planetesimals form, but they also, they're also indicative of other processes going on the disk. For example, if there are planets in the disk, then they would eject planetesimals or scatter them onto high eccentricity orbits. So one of the things we did in preparation for this was to run a suite of n-body simulations to determine what kind of structures would be imposed on the disks. Because one of the things we were expecting is that these are Kuiper belt analogs, so there would be a Neptune mass planet at the inner edge, so we could use the shape of the inner edge to tell us what the mass of the planet was that's sitting at the inner edge. And we found that actually this is not necessarily the case, because what you can see from these simulations is that the shape of an inner edge carved by a planet is very sharp, and most of the disks that we see have much shallower inner edges. Some of them are sharp, but many of them are much shallower, and that's not consistent with being shaped by a planet at the inner edge, but rather by collisional erosion, because collisional erosion would have depleted the inner edge of the belt much faster than the outer edge. And we're also getting from these high-resolution imaging information on the vertical structure in the disk. So you can see, intuitively, you can understand that you get this from an observation of something like HD 32297, which is an edge-on disk, so we can measure the vertical height here. This plot shows the scale height, h over r, as a function of age, and all the grey dots are the observations taken from the regions, the lower resolution survey that we did first. We can see that the scale heights here are of order between 2% and 20%. And what this means is if the disks are being puffed up and they're being stirred by embedded bodies that are sitting in the disk, then it's telling us that those are of order 100 kilometers in size, because disks get stirred up to the escape velocity of the biggest bodies. So it's telling us something about the biggest objects in the disk, which otherwise we'd have no information about. And now we're looking at arcs we have much higher resolution. We find that find even narrower disks like this one, HD 32297, that has a scale height that is down at a percent. The pink points on here are the ones from the higher resolution arc survey, and this makes the scale heights comparable with the scale heights seen in protoplanetary disks. Now, in protoplanetary disks, the scale height is set by settling of the millimeter-sized grains down due to interaction with the gas. There's not so much gas in these systems for that to be going on, but it could mean that the planetesimal belts inherit the scale height from the protoplanetary disk. For some disks, we have the scale height, and we can look at this as a function of wavelength. Some disks have been imaged at multiple wavelengths, like beta-pic. Beta-pic has been imaged from the millimeter all the way to the mid-infrared, and what Yino has found is that the scale height of the disks varies with wavelength, so that the disk, when seen in the millimeter, which traces millimeter-sized grains, is narrower than the scale height of the disk when seen in the mid-infrared, which traces micron-sized dust grains. And this is counterintuitive. It's not what we expect. We expect the disks to be thinner when you look at smaller dust grains that might be affected by settling by gas drag or by collisional damping. So I say that we have gas in some systems. This is just one example. It's HD 1216117. We've got a narrow planetesimal belt, and we also have carbon monoxide gas that's seen at the same location. This fits neatly within the paradigm as long as the planetesimals are made up of volatile ices, so that when they collide, they release those volatiles into a gas disk that then viscously spreads and ultimately photodissociates and viscously spreads and accretes onto the star. So you can explain these observations very nicely within that, but we're keeping an open mind because there's still a niggling doubt in the back of everyone's minds about whether some of this gas could be primordial, and in fact there's a lot of hydrogen around. And there could be evidence from this in the structure of the dust, actually, because the dust structure has a clump at this location in the disk, and we were exploring two models to explain this. In the first one, it fits neatly within the paradigm. There's a planet orbiting at the inner edge of the disk, planet migrates outwards, traps planetesimals in resonance, and that causes a clumpy structure that fits with what's observed. But another explanation could be that actually there's lots of gas around, and all the dust is being moved around by the gas, and if there's a vortex in the gas disk, then that could equally shape the dust disk, and that could also explain the observation. So we'll have to wait and see which ones of these explanations is correct. Okay, so before I finish, I wanted to give you show you some of the exciting JWST results that are coming out. These are a couple of results on beta PIC that are showing that debris disks, while I've been explaining them in a paradigm where everything is evolving in steady state, some debris disks are very dynamic environments. For example, ESA's image of the mid-infrared imaging finds this new structure which she calls the cat's tail. It's made of micron-sized dust grains that are inferred to have been created some of order a century ago in a collision between Mars-sized planetary embryos at this location in the disk, and we're seeing the small dust grains that are getting ejected from the system. And a similar result comes from Christine, who has looked at the spectrum of the disk in this region here and compared it with what was seen 20 years ago by Spitzer, and sees that the dust that was seen by Spitzer has disappeared. In particular, the micron-sized dust grains in that region have disappeared. And the interpretation there is that there's been there was a collision that happened just before the Spitzer observations of micron-sized dust grains that are then getting expelled, presumably creating another cat's tail that's probably still in the closer in and still forming. But probably the neatest result that I've seen from JWST is this result from Andras Gaspar, which shows the Fomalhaut disk, which with ALMA we see as a planetesimal belt, and then there's a cleared inner region here. But when you look with JWST, you see that this inner region, where we thought there'd be planets, which is why there's nothing there, is actually filled with dust. And there's also even tentative evidence of an intermediate dust belt. And this is neat because it actually applies to every star that we've looked at so far. There's also Vega, HD 107146, Epseri. There's results going to be coming out over the next year that will show that this is a common feature. We think that this actually is explained within the context of the paradigm as well, because the radiation forces that expel the dust also have a drag component that brings the dust in towards the star. Now, I wrote a paper 20 years ago that said Pointing-Robertson drag is insignificant, but it's only insignificant in the sense that most of the dust collides and gets broken up before it moves very close to the star. But there's always some dust that leaks in, and Jess made a model of how much dust leaks into this inner region that Max has been applying to that observation of Fomalhaut, and finds that we can fit perfectly all of the observations. This is the SED of the system. This is the surface brightness of the disk as a function of distance. We can explain all of this dust that's in the inner regions by dust that's getting dragged in by Pointing-Robertson drag. And then you can also explain the intermediate belt if there are planets in the middle of the system at about 80 AU that are trapping dust into resonances as they go past. And you can explain the fact that there's an absence of dust within 20 AU if there are giant planets within there that are ejecting the dust as well. And so the last thing I want to say is to explain, give a pitch for why you should care about this dust. Not just because it's interesting because we can tell something about the planets in the system. It's also scientifically interesting because, well, Craig showed earlier this year how the dust that got accreted onto the Earth early in its history might have created the conditions that were important for the origin of life through geological processes, also concentrating that dust. But if you don't care about it from the scientific point of view, pragmatically it's very important, because if there's dust in these inner regions, then it can cause problems when you try and do exo-Earth imaging. This becomes problematic when the level of dust in the system is more than about 10 times the level of dust in the solar system, which would be down here. Now, we know from photometry that very bright dust, more than 10,000 times as bright as the solar system, is rare, about one in 1,000 stars has dust that's that bright. And we've done ferrometric nulling interferometry studies with LBTI and have found that dust that is about 100 times the level of the solar system is found around 26% of stars. And we don't know how many stars have dust that's going to be problematic for exo-Earth imaging, but this function here could actually turn over, and it could be quite problematic. Now, that's a pessimistic note for some people. It's optimistic for me because I'm very excited about the science we can do with this dust. Anyway, I think I'm out of time, so I'll just leave it there. Take questions.